Pause the video and read the question. This will be a long question, so prepare yourself mentally for it. We want to find the minimum acceleration, the minimum amplitude that the tightrope walker will have to impart to the rope so that the ant is momentarily weightless. So we want the maximum acceleration of the rope upwards and downwards to be G, so that when the rope comes by the ant and it's moving down, if he gets in a trough, then the acceleration from the rope will be G and he'll be in free fall right above the rope. Recall that our equation of a wave in the XY direction, or XY coordinate system, if the wave is traveling along the x-axis, then y represents how far up or down the wave is moving at some time t in some position x. We want to find the acceleration in the y direction. So first we need to find Vy. So this is not the wave speed. This is not related to the wave speed at all. The wave speed is how fast energy travels along the wave in the x direction. This is how fast the wave itself is moving. Particles themselves are moving up and down in the y direction. This is V in the y direction. So we know velocity is a derivative, but we have a function of two variables here. So we'll have to take the partial derivative of y here with respect to t. So partial derivatives you may not have seen before. To do a partial derivative, t is our variable here. We treat everything else as a constant. So x is just a constant if I'm doing partial y with respect to time. So I want to take the derivative of this. All of this here is just constant. T is the only variable. So derivative of cosine is negative sine. That's where the negative sign comes from. Times the derivative of the inside. Well, derivative with respect to t of omega t would be omega. So we get an extra omega outside. The derivative of this, negative kx, with respect to time is 0. This is a partial derivative. Okay, we play that game one more time. The acceleration in the y direction. This is how much the rope is accelerating up and down. Is this the partial of v with respect to t? So we take another partial derivative. Derivative of sine is cosine times the derivative of the inside. The derivative of omega t, we get an extra omega outside. So here's our acceleration function. So every point along the rope is accelerating up and down. This tells you how much at some time and at some position x. The maximum of that says A max. The typesetting's a little off there. The maximum acceleration, maximum of cosine is just the number in front. So in magnitude, the maximum acceleration is A omega squared. We want that equal to G. So just solving here for A, the amplitude, the minimum amplitude would be G over omega squared, where omega is the angular frequency. Remember here in our original, there should not be an omega there. That's a typo. So ignore that omega. I'll fix that in the document. But I'm not going to restart. I've already restarted this video 5 times. So this should be A cosine omega t minus kx. The period is 2 pi over omega. That's how much time it takes to make one complete cycle. The wavelength is 2 pi over k. That's how much distance it takes to make one complete cycle. So omega is 2 pi over the wavelength. K is 2 pi, omega is 2 pi over the period. K, the wave number, is 2 pi over lambda, the wavelength. So we need to write omega here in terms of our givens, the tension, the wavelength, and mu. And then we'll plug all that in and we'll get a minimum. So recall, for a string under tension, the wave speed, v, that's completely different from this v. This was the up and down speed. This is the transverse speed, the wave speed, how fast energy is moving along the string. This is horizontal. This is in the x direction. And that goes like the square root of the force, in this case our tension, divided by our linear distance, or linear density. But V also equals another formula for the same V is lambda times F. And F is, like we just said, omega over 2 pi. So putting these two together and solving for omega squared, because we have an omega squared here, I thought it would be simpler. I solved this for omega squared. Pause the video and check that yourself. Put these two together and plug in here to get this here. So check all these details yourself. This is the minimum amplitude that we need so that the ant will be momentarily weightless.